everyone. So my name's Helen Byrne. I'm one of the managers of one of the AI engineering teams at Graphcore. Graphcore is a British chip startup. I'll tell you a little bit more about what we do, and I want to introduce some examples of where we've been accelerating AI in finance. So why do we need a new processor? So we've designed a brand new processor for AI. So why do we need that? I'll introduce the technology and go through a few examples. So I really like this paper. So this paper was published a couple of years ago by Sarah Hooker from Google. And she introduces this idea of the hardware lottery. So it's a term to describe why a research idea might be successful. And she describes it might be successful purely because it's a good fit for the hardware and or the software that's available. So this is quite like an interesting idea. So you might come up with a brilliant research direction, but actually it doesn't fit to the available hardware or software today. And so that research direction doesn't become a success. So maybe we need something new, something more flexible to use. We find in financial modeling, when we speak to people, that often you have to use oversimplified models because you need to achieve this competitive latency and fight the noise in the data. So Jeff Hinton here as well, for those of you who, I'm sure you all know this, who he is, but he's the godfather of deep learning of AI. He won the Turing Award a couple of years ago. He, very fortunately for Graphcore, he was asked by Wired magazine, how do we build the machine learning systems of the future? And he pulled out of his pocket a Graphcore chip, which he had received at NeurIPS previously. And he said, we need something different, we need something new, and I've got it here. I think this is the future. So even Jeff Hinton thinks we need something new to push the next boundary in innovation. So who is Graphcore? We're a hardware company. We design computer chips. So that's that piece on the left. But we also co-design the software to go with it. So unless you can use these chips easily, no one's going to use them. So we're a software company really as well. In fact, most of the engineers that work at Graphcore are software engineers. And then we also design the platform. So we don't actually sell the chips. We put them into boxes, into 1U pizza boxes, and you can fit them into your data center. So this is what we build. And why did we design something new? So we've designed a processor for a brand new workload. So machine intelligence represents this new compute workload that's required. And we've kind of used these as the sort of design inspiration for what this should look like. So machine intelligence, artificial intelligence models, they exploit massive parallelism. There's also sparsity in data structures, like graphs, which are inherently sparse. We can use low precision compute, so we actually quite like to have a lot of stochasticity. Model parameter reuse. We have convolutions, recurrent layers, so lots of parameter reuse. And we look at this static graph structure like the brain. So ultimately, the compute graph is static, and we want to fire different neurons for different tasks. So what does that look like? I'm going to give you just a quick high-level overview of the technology of what it looks like. And if anyone has more questions about this later, then please feel free to ask. So I want to show you the difference between the traditional technology and an IPU. So I've just realized that I haven't actually introduced the name of the Graphcore processor. So IPU is the intelligence processor, which is the Graphcore processing unit. CPU, obviously, GPU, you know. So in terms of parallelism, CPUs were designed for scalar processors. You can send an email, you can open a browser, you probably have a few cores, you can do a few of these at one time. GPUs, designed for graphics originally, actually been very well repositioned and useful for AI as well. They're designed with a SIMD architecture, so there's single instruction, multiple data, multiple thread. They're really good at processing vectors. So they're designed for these contiguous, dense blocks of data, like pixels, like graphics. IPU, so this is our processing unit. It's a MIMD architecture. We want to exploit massive parallelism. We've actually got nearly 1,500 compute cores on our chip, and each of these runs an independent process. And each of those cores has 6 threads, which also run independent parallel processes. So we have about 9,000 independent parallel processes that you can run at one time. The other major difference is in the memory side. So we think for AI, for machine intelligence, you really need high memory bandwidth. So on the left here, you have the CPU with the off-chip memory. This also uses quite a lot of power because you're constantly moving on and off chip. GPUs have these small caches right next to the chip, to the compute cores, like your L2 cache. And then they have this large amount of, well, in the latest sort of state-of-the-art GPUs, it might be HBM, a lot bigger, still high bandwidth, but off-chip. Then the IPU, so the difference here is we've gone for highest bandwidth memory possible. We've actually distributed the SRAM across the whole chip. So you have this memory coupled with the compute. You get 65 terabytes per second of memory bandwidth here. So it's, order of magnitude faster than anything else you'll see. And just, again, I won't go into too much detail here, but just so you know, you can use these chips like you use CPUs and GPUs. So if you're used to using the ML frameworks like TensorFlow and PyTorch, we support those. There's a lot of other libraries that aren't listed on here as well that we do support, like Hugging Face for NLP. And yeah, so we have our own software stack called Poplar, which is also open sourced. The Poplar libraries are open sourced. And we fit in with the data center kind of virtualization and integration software as well. So we want these to be really easy to use. So let's have a look at some examples that we've worked on in the finance area so you can see how IPUs can accelerate the workloads. So first of all, MCMC, not anything really typically new. I understand it's not typically kind of deep learning innovation, but typically it might not be used, and you oversimplify models, and you might not use MCMC. So this is a quote here, a customer that we worked with before called Carmot Capital, where they were finding that they were using simplified models that weren't good enough at modeling the noise in the data. They wanted to use MCMC, but it just wasn't fast enough, efficient enough to train the models. So I'll show you in the next few slides, but they were able to train their model much faster on IPUs and retrain their model as well. So the problem here is alpha estimation. Typically, you could use something like linear regression, but linear regression has limitations. So obviously, it doesn't model the noisy data well. You're not able to see the non-linearities, the relations in the data. So MCMC, now you're going to predict distributions instead of just point values. And this helps us to avoid overfitting. It helps us to handle the non-linearities in your noisy data. So just to talk about the computation that's required here, so you can kind of see why this works well on IPUs. So here you have, you can think of Hamiltonian Monte Carlo. You have this hockey puck on your surface, and it gets kicked in a random direction, and it stops, and then it gets kicked in another random direction, and you have to calculate the gradient of the slope on your surface, and update your momentum, and find the new position of your hockey puck. I think this is going to move around a bit. So you can see this is a very sequential algorithm. It's very step by step. And here, having the memory and the compute, so the high memory bandwidth, is really, really important. And it's kind of critical to run this kind of sequential algorithm efficiently. So you get really nice results from this HMC algorithm, but it can be prohibitively slow because it's step by step. So this is something that IPUs can speed up because we have this 65 terabytes per second on chip. So this is the Carmot Capital model that was run. So this is their model. It's written in TensorFlow probability. They run it on the latest GPU that they had access to. This is to train the model. In the footnotes, you can see a few more details, and this is also on our website. It's a small 3-layer, fully connected neural network. And if you run this to train this on their GPU, it was taking nearly 50 hours. And the same model, exactly the same model in the same framework, running on IPU was about 3 hours, just under 3 hours to train. So what this means is they're able to retrain constantly instead of having to wait a really long time to see the insights. Next example, LSTMs. So LSTMs or RNNs, recurrent networks, can be used for time series analysis. So this is now moving more into the deep learning realm, I guess. So they're really good at modeling time series and sequences. They can be used for a number of different finance applications, but price prediction is a really kind of common one. I won't kind of give you a lesson on LSTMs, but this is a kind of overview schema of an LSTM, obviously. It's a recurrent net. It's a bit more complicated than a simple RNN. You have this internal state that you see running along the top. This allows us to model longer-term dependencies than you could with an RNN. The gates that you see here, the forget, you can decide what to forget, what to update, and what to output. It's a better way of modeling longer time series than a recurrent net, than just a simple RNN. Ultimately, though, it's recurrent, so it's, again, sequential. And then this, again, means that having the high memory bandwidth is really critical for these types of models. So LSTMs, RNNs, GRUs, they can run really much, much faster, much more efficiently on our chips, because they sit, the weights activations, they sit on the chip. They're not streamed on and off. So one paper, some research that was done last year with Oxford Man Group. Well, Oxford Man Group did the research. It was on Graphcore's IPUs. So the paper's on arXiv. There was an article on Bloomberg about it. They developed a model. It's built of convolutional layers and LSTMs. It's to model the price movements for limit order books. He found, because the quote, they found they could run this model 5 times faster on IPUs than they could on the GPUs that they had access to. So the paper is on arXiv. There's a blog about it on our website and obviously some press about it as well. Natural language. So NLP is really ubiquitous in all industries now. We're seeing it everywhere. It's really important in finance, obviously. There's endless applications in fine-tuning tasks. A couple of quotes here. JP Morgan have said they're using Graphcore's IPUs to kind of research and develop their NLP and see how it can be used in their research. BURT. So BURT is that kind of original model, breakthrough NLP model. It's actually probably the one that's most widely used in production still today. Obviously, we're moving to these huge GPT-style, huge NLP models. But actually, in production today, we see BURT, even though all the BURT variants as well, Distill, BURT, Roberta, all of them. But BURT is still really widely used. It was developed by Google. It can be used for a whole host of fine-tuning tasks. And we've run BURT on IPUs for a while now. We took part in the MLPerf benchmarks. If you know about the MLPerf benchmarks, BURT is one of them. We're the only startup that have actually submitted to that. So we can run BURT pre-training at nearly 2x the speed as that you can run it on a DGX. And that equates to actually nearly 2.5 times the performance per dollar, because a iPod IPU system, pod system is cheaper than a DGX system. Again, these performance benchmarks, you can find more details on our website. This is the pre-training phase 1 throughput. And then on the inference side, so inference obviously is very important. In this plot, you want to be bottom right. So throughput is further, better throughput is further to the right on the x-axis. Latency, you want to be lower on the y-axis. So here, this is comparing against NVIDIA's results that they've published on their website and the results that we publish. So we're able to run, the red line with the blue dots is our latest generation chip. We're able to run inference, BURT large inference with 22 times higher throughput and 8 times lower latency if you compare FP16 results. And then if we compare our FP16 with TensorRT int8 results from NVIDIA, which obviously means they're using half the precision, and the TensorRT optimizations, we're still nearly 3 times higher throughput and lower latency for the compared, and we're using FP16, so you don't lose that accuracy that you might do for converting to int8. So BURT is something that we use a lot on Graphcore IPUs with a lot of customers in a lot of different industries, but finance is definitely one of them. And we do have a research team at Graphcore, so we are looking at innovations in NLP Transformers. How can we make these transformers more efficient? They take a lot of compute to train. They're only getting bigger and bigger and bigger. They're very dense. So there are a few papers that have been released from Graphcore research. Packed BURT is a packing algorithm just to make the data packing more efficient, so you're not padding the sequence length with a load of zeros. Group BURT introduces a group transformation, sort of inspired by group convolutions, that give you the same performance for less flops. And sparse BURT, this is something we're really interested in at Graphcore. Often use sparsity at inference time. You might prune and then run something with a lower, like a lighter model with fewer parameters, so you can get that latency, better latency at inference time. We're actually interested as well in the training of these models in a sparse way. So this paper is on dynamic sparse training, so you're actually changing the sparsity pattern during training. It's not fixed. So yeah, again, we've got a section on our website about all of the research that we've done in this area, but this is a big, big focus for us. And last one, this is probably more suitable for next door because I saw that there is a insurance track. So this is related to insurance. So I'll skip through it quite quickly. EfficientNet is the state-of-the-art image classification model, really, one of the, and it uses these group convolutions. Very quickly, group convolutions just mean that you're splitting the channels. So a normal convolution, you do across all the channels of your input or your activations that you're feeding in. Group convolutions, you do it in groups of channels, or fully depth-wise convolution, that channel dimension is just 1. These types of new models where you need this more fine-grained parallelism. So you remember IPUs are MIMD compared to other processors which are SIMD. So we have like we're able to process these smaller blocks, these smaller kernels much more efficiently. And that's what you see here with EfficientNet. When you've got group convolutions, we're much faster to run these types of models than you can run it on a SIMD processor. And the last example is with another UK startup called Tractable. They're an insurance startup, and they use EfficientNet on IPUs to speed up the training of their models so that they can classify car insurance claims faster, basically. Again, more in the press and on our website if you want to read more. So in summary, you can use IPUs for training and for inference. For inference, you can get your results with lower latency. You can use more complex models. You can reduce TCO. At training, you can speed up training, so you can train more often, and you can accelerate your research. And yeah, if you want to read more, please follow us and have a look online. And if anyone has any questions, let me know.